Okay, good afternoon. As promised, let's do one problem where we can fully use the complete matrix method that we have developed. So we can see what the use of it is. So to do this, let's pick an optical system. So let's say we have a converging lens and a diverging lens. So let's say we have a lens, converging lens. Let's say then we have let's say we have a diverging lens here, right? And let's say this is the optical axis. Let's say we have an object here, right? And let's say the focal length of the converging length is 20 centimeters, right? And the focal length of this is, let's say, it's 10 centimeters, right? And then they say that this is 40 centimeters. The object, this is the object. The object is 40 centimeters from the optical system. So essentially our optical system is both this converging lens and the diverging lens. One has focal length of 20 centimeters, another has focal length of 10 centimeters, and they are separated by a distance of 8 centimeters, right? And then um, yeah, so this is the information that we are given, and let's also say the height of this object is 1 centimeter. So this is the optical system that we are given. The optical system consists of two lenses, a converging lens of focal length 20 centimeters, a diverging lens of focal length 10 centimeters. The image is the object is placed uh, 40 centimeters from the optical system with a height of 1 centimeter. So now what we have to determine is we have to calculate, position and size of the image, right? So we have to calculate the position and size of the image. So if you were to do this with the ray tracing technique, then you would basically go through the convex lens, then you would go through the concave lens, and then you will have to figure out where the image is, right? And then you will have to measure the height of the, then you will have to measure the actual distances, right? And then figure out what would be the you'll have to use the equations that you derived, like 1 over v is equal to 1 over u plus 1 over f, and that's how you would derive it. But in case of matrix method, right? So essentially, first from you're going to go from your object to the convex lens, right? So the first matrix is just simply translation, right? From object to the convex lens. So from object to convex lens, from object to convex. That is simply translation. Once again, the translation matrix is 1, 0, the distance divided by the refractive index 1, and the refraction matrix is 1 minus power 0, 1, and the system matrix for thin lens is 1 over f 1 over f 0, 1, right? So from object to convex lens, you just have a translation of 40 centimeters. So we just have, and that is in air, so 1, 0, 41. And then you have the convex lens itself, and if it's a, and here we have a thin lens, and here we have a thin lens, so that would be a thin lens of 20 centimeters. A convex lens is a positive lens because it's converging. Remember, I told you this in the very first lecture, to have a back of the envelope ray diagram, right? if you have three rays going through this, right? The middle ray takes longer time, so it converges, right? Whereas if it is going through this, it diverges. Recall that. So convex lens is a converging lens, so the focal length is positive, right? So you have one. Uh, so this should be minus one over um, f. So here you should have just minus 1/20. Um, 0, 1. And then you have again a translation of 8 centimeters. So you have 1, 0, 8, 1, right? And then you have the concave lens. So that's going to be negative of negative. So you're going to get positive, right? So you're going to get negative of negative, that is positive 1 plus 1/10, 0, 1. So that's the whole system matrix. So now then you have one more translation actually, that is to go from the concave lens to the image. So if the image is at a distance v, right, then you have the final translation from the concave lens to the image. So that would be 1, 0, v1, right? So the total system matrix would be a product of all these. This would be what we call as the door-to-door matrix in lecture 11. So if I combine all these things, I would basically get this matrix if I write it as such, because there is the unknown v. And if I multiply all these matrices with known numbers, I am basically going to get something like 2.2, 0.01. Let me just write it here. I'm going to get 1, 0, v1, 2.2, 0.01, 32.6. Right? That's going to be the net matrix going from object all the way to the image. So if I finish this multiplication as well, I'm going to get something like 2.2, 0.01. Then I'm going to get 2.2v plus 32.6 plus 0.01. This is going to be the total system matrix going from object to the image. This is what we called as the door-to-door matrix. Remember that here we had the optical system and we went from the object through the optical system to the image. We did a translation here, we used the system matrix, and we did another translation here, right? We combined all these things and made one matrix, right? And we call that matrix, we got that as B plus AD1 minus A0 C minus AD2. This is how we got that matrix, and we got this as 0 by with the condition that ray emanating from the axial point necessarily ends up at the axial point, right? You should go back to lecture 11 and take a look at that again if you don't understand that, right? So this element should be 0 no matter what in the total system matrix. So this element should be 0. So therefore simply 2.2v plus 32 should be 0, or you would get essentially v to be minus 14.5 centimeters. So you got a negative sign. What does that tell you about the image? Recall the sign convention that if you get a negative sign, that means the image is onto the left of the concave lens, right? Because because it is onto the left, you got a negative sign, and then you can get the magnification, right? This is nothing but the magnification. Recall, we saw that this is 1 over m and this is m. Please go back to lecture 11 if you don't recall this. We saw that these matrix elements are 1 over m and m. So then magnification is simply 2.2, right? So you don't even need to do any math. You can just see that magnification is 1 over 2.2, because this is 1 over n, right? So we have a system, here, and using our matrix method, we were able to very nicely uh, uh, do the multiplication, and get to a stage where we could get the image distance, and we were also able to get the magnification. The important things to remember is that this term and this term, we saw that they are magnification and reciprocal of magnification, from the fact that determinant is equal to of any optical matrix element, matrix is equal to 1, and this we saw while discussing the unit planes, right? So from here we were able to very easily get the image distance, and we were able to get the magnification also very easily, right? So now you can also, now that you have the matrix elements, you can also determine very nicely, you can also determine what would be the unit planes, for example, for this system, where the unit planes would be. And you can basically, just based on this matrix, you can completely understand the entire system, right? So that's how we can effectively use matrix method to have a complete understanding of any optical system. Thank you.